Welcome to Chapter 2 of the Graph Neural Network series. Today we dive into graph convolutional networks, or GCNs, which revolutionized how we apply deep learning to graph-structured data. We'll start from the mathematical foundations in spectral graph theory and build up to practical implementations. By the end of this chapter, you'll understand why GCNs work and be able to implement them for node classification tasks. Let's start with the fundamental challenge. Convolutional neural networks work beautifully on images because images have a regular grid structure. Every interior pixel has the same 8 surrounding neighbors, always in the same spatial arrangement. We can slide a 3x3 kernel across the image knowing exactly which pixels to include. But graphs are different, they have irregular structure. One node might have 2 neighbors while another has 100. There's no natural ordering of neighbors, no up, down, left, right. And the distance metric isn't Euclidean, but defined by paths through the graph. This means we need a fundamentally different approach to define convolution on graphs. The graph Laplacian is our mathematical key to understanding graph structure. It's defined as L equals D minus A, where D is the degree matrix with node degrees on the diagonal, and A is the adjacency matrix. The Laplacian has remarkable properties. Every row sums to 0, it's positive semi-definite meaning all eigenvalues are non-negative, and it completely encodes the graph's connectivity. Through eigenvalue decomposition, we can express L as U times lambda times U transpose, where U contains the eigenvectors and lambda contains eigenvalues. These eigenvectors form a basis for signals on the graph, analogous to Fourier basis functions for regular signals. Here's the beautiful intuition behind spectral graph theory. The eigenvectors of the Laplacian represent different frequency components on the graph. The first eigenvector, corresponding to eigenvalue 0, is constant across all nodes. It's the lowest frequency, no variation. The second eigenvector varies smoothly across the graph, grouping similar nodes. This is why it's used for graph partitioning. Higher eigenvectors vary more rapidly, capturing finer details. Think of it like the Fourier transform for images. Low frequencies capture overall structure, high frequencies capture edges and details. For graphs, small eigenvalues mean smooth variations across neighbors. Large eigenvalues mean rapid changes. Now for the heart of GCN, the layer formula. H superscript L plus 1 equals sigma of A hat times HL times WL. Let's break this down. HL contains node features at layer L, 1 row per node. WL is the learnable weight matrix that transforms features. A hat is the normalized adjacency matrix that handles aggregation. Sigma is the activation function, typically Ray LU. The key insight is that multiplying by A hat averages each node's features with its neighbors. The normalization in A hat, which is D tilde to the negative half times A tilde times D tilde to the negative half, where a tilde is a plus identity for self-loops, ensures that the aggregation is properly scaled regardless of node degree. 2 design choices make GCN work well in practice. First, we add self-loops by computing A tilde equals A plus I. This ensures that when we aggregate neighbor features, we also include the node's own features. Without self-loops, a node's own features are dropped from its update entirely, only neighbor features survive, and an isolated node with no neighbors would end up with nothing at all. Second, symmetric normalization scales contributions appropriately. Without normalization, high-degree nodes would dominate the aggregation. The formula D tilde to the negative half times A tilde times D tilde to the negative half normalizes both the sender and receiver by the square root of their degrees. This keeps the matrix symmetric, which is numerically stable, and bounds eigenvalues between negative 1 and 1, preventing exploding or vanishing gradients. Let's walk through the GCN computation step by step. First, we perform feature transformation. Multiply the input features H by the weight matrix W. This projects features from dimension D in to D out. Second, neighborhood aggregation. Multiply by the normalized adjacency A hat. This averages each node's transformed features with its neighbor's transformed features. Third, optionally add a bias term. Fourth, apply the activation function, typically ReLU, to introduce nonlinearity. The dimensions flow from n by d in input features, through the weight matrix to n by d out, unchanged through aggregation, and out as n by d out activated features. This is one layer, stack multiple layers for deeper graph reasoning. PyTorch Geometric makes GCN implementation straightforward. Import GCN conv from torchgeometric.nn, create a layer with input and output channels, then call it with node features x and edge index. The edge index is key. Instead of a dense adjacency matrix using O of v squared memory, PyG uses coordinate format, written COO, which is a 2 by E tensor where each column is one edge given as a source and a target node index. This is crucial for large sparse graphs. The data object packages everything together: X for node features, edge index for graph structure, Y for labels, plus train, validation, and test masks for semi-supervised learning. This clean abstraction lets you focus on model architecture rather than data handling. The Cora dataset is the standard benchmark for GCN evaluation. It's a citation network of 2,708 machine learning papers with 5,429 citation links. Each paper has a 1,433-dimensional bag of words feature vector and belongs to one of 7 research areas. The task is semi-supervised node classification. Given labels for only 140 training papers, classify all papers. A 2-layer GCN with 16 hidden units achieves about 81.5% test accuracy, the reference figure reported by Kipf and Welling. Projecting the learned embeddings down to 2 dimensions shows papers from the same category clustering together, which tells us the model has captured both the word features and the citation structure. Training runs for about 200 epochs, with the loss decreasing smoothly and validation accuracy usually plateauing well before the budget is exhausted. Let's summarize what we've learned. The graph Laplacian provides the mathematical foundation for spectral analysis of graphs. GCN extends convolution to irregular graphs through normalized aggregation. Symmetric normalization ensures stable, well-behaved learning. PyTorch Geometric provides efficient, easy-to-use implementations, and GCN achieves strong performance on node classification benchmarks. One challenge to be aware of is oversmoothing. As we stack more layers, node representations become increasingly similar, eventually losing all distinguishing information. In Chapter 3, we'll explore message passing neural networks, which provide a general framework that encompasses GCN and many other architectures. See you there.